Today we will solve day 8 of Advent of Code. And I have to say, in this quiz the instructions were a little hard to read, but I try to make you understand. So I've copied this test input over here. So we again get a grid, and on these grids are antennas, right? So these symbols over here represent antennas. In this example we have two kinds of antennas, 0 and A, right? And these antennas can basically send signals to each other, right? And then they can create an antinode. And an antinode is basically, let's see, for example, these 2 points, right? We have to go 3 to the right and 1 up, right? So the antinode of this point would be 3 to the right, 1 up, would be here, right? And the antinode for this antenna over here would be the opposite, would be 1 down and 3 to the right, okay? Would be here. As you can see, these are in a perfect line, right? Now let's see these two over here. So as you can see, we go 1 up and 2 left. So 1 up, 2 left would be here. Here we go 1 down and 2 right would be here, right? And let's also do these two. So 1 right, 2 up. Now as you can see, 1 right, 2 up would be out of bounds, right? So we don't put here any antinode, but over here we can. 2 down and 1 left, it would be here. Now here is another antenna, but it still counts as an antinode. We still have to count that, right? Even if there is an antenna over it. And when we do that for all the points, let's also do here AA. As you can see, 1 up, 1 left, 1 up, 1 left. Here would be the antinode for this point, and here would be the antinode for this point, and so on, right? And then we create the antinodes for all these points, for example, these two, and these two, and these two, and then these two, right? All of them. And then we should have something like this, right? These symbols over here represent antinodes, okay? Now the logic is not that hard. How do we find the antinodes? Let's take these 2 points, right? So we have 1, 8, and we have 2, 5. These are 2 points, right? Now we have to find the antinodes. What we do first, let's first take the antinode of this first point, 1, 8, okay? What we do is we subtract this point from this point, okay? So we would have -1, right? So 1 minus 2 would be -1, and 8 minus 5 would be 3, okay? So this represents the offset. What we now have to do is we have to add it to this point, right? So 1 plus -1 would be 0, and 8 plus 3 would be 11. And that is the point of the antinode of this first point, right? So 0, 11, okay? Over here. And that is correct, right? 3 to the left, 1 up, 3 to the left, 1 up. Now for the second point, this over here, we do basically the same thing. So we subtract this point from this. So 2 minus 1 would be 1. And 5 minus 8 would be -3. Again, we get the offset. Then we add together. We have 3, and 5 plus -3 would be 2, right? So we have row 3 and column 2, right? As you can see, this is also correct, and they are all on the same line. And that's basically it. So I structured this project over here with a struct map representing this map over here. We have the grid, a vec of U8, like we did before, and antennas. So antennas is a hash map. So for example, let's say we have let's say we have this hash map antennas, right? And as I've said, we have different kinds of antennas. So we can't create antinodes for A and 0. They both have to be the same kind, right? So what I want to do is we have this hash map antennas, and in the hash map we have key value pairs, right? So the first one is new8, basically representing a character in ASCII. So let's say we have 0, and then inside, and then as value, we have another vector of points, right? So I want 0, and then all the points of the antenna with the symbol 0, right? So we would have 1, 8, we would have 2, 5, we would have 3, 7, and so on, right? This would be the first entry. Okay. And then in the next entry, we would have A. We would have A, and A would have points 5, 6. It would have 8, 8, and it would have 9, 9, right? And so on. And this we do for all the symbols we find in the map, right? So in the test input, we have only 2 kinds of antennas. And that's basically it. So let's see the code. Okay, we start at part 1. And we want to parse, so we can then put map from, and we take the input, right? So first of all, we create the map struct. This will be grid of vec of u8, right? And the antennas hash map of u8 and another vector of points. Okay. And we haven't created a point, so let's do that. Struct point i32, i32. And let's also derive some stuff because we will need it for the hash map. So let's do clone, copy, default, hash, and EQ. Okay. Then let's start with parsing the input. So as usual, we implement from string slice for map from, let's call this puzzle, returning self. Let's start with the grid. So this would be of type vec u8. We did this before. So we take puzzle, we iterate over the lines, we map. So for each row, take bytes, collect the inner vector and collect the outer vector. Okay. Then let's do antennas. So we take the grid we created. So we take this grid we created, we iterate, we enumerate to get the indexes. And let's do a flat map. So we get the index and the row, basically the vector of columns. And then we iterate over the row, enumerate. Let's do filter map. And here we have Y and the cell, right? So if cell is not a point, a dot, then we return a tuple with the cell, meaning the symbol, right? For example, A or 0, and the point X as i32 and Y as i32, right? That's it. And then we can fold to hash map new, and for the accumulator, let's call this antennas. And for the element we are iterating over, we can destructure it. So we have the symbol and the positions, right? And then antennas.entry. So we look, is there already an entry for the symbol, for example, antenna 0, right? If we already have inserted one point with the symbol 0, then we can just insert. Or if it doesn't exist, then we insert with a new vector, we create a new vector, and then we push the position to this vector. And then we return antennas, right? Like this. And then in the end, as you can see, antennas will hold a hash map of U8 and a vector of points, right? So then we over here construct this self-grid and antennas, right? And we have to move over here. So this X will be moved inside this closure, right? Because we are using it over here. Okay, that's the first step. Now we have parsed the input, right? Map is now of type map. That's good. Then what I want to do is I want to call a signal on this map, right? So map.signal. And let's create this method. So we implement that for map. So this will be the signal method. And we return a hash set of points, right? Basically, this will be the positions of the antinodes. So antinodes, and we create here a hash set, because if we have an antinode at one position, then if we have another antinode from other points, but at the same position, then we will not count it 2 times, right? We still count it 1 time. Okay, so, and I will also create a function get pairs, right? So let's do that. Fn get pairs. Take a reference to self, and we return a vector of tuple holding 2 points. Okay. And all we do basically is we iterate over the antenna's values, right? Over this vector over here. We don't need to know which symbol, right? We don't need to know at that point. But we have to know the values, basically the points of these antennas, right? Then we do flat map. So for each antenna, and this will be of type wake point, right? This over here. For each antenna, we iterate over the vector, and we do another flat map. So we get point 1. And then again we iterate over antenna, and we get point 2, right? So we return P1 and P2. Then we filter P1 is not P2, right? So we do that. Let me show you what we are doing here. Basically is we iterate over the points of antennas, right, over these here, and then we take another vector, right? We take this point 1, 8, and again in this same vector we take 2, 5, right? So this will be 1 pair. As you can see, this is the outer, this is the tuple holding 2 points, right? And then we have 1, 8 and 3, 7, right? And then the last one would be 2, 5 and 3, 7, right? So that is what we are doing over here. We are basically iterating 2 times, and we are combining these points together. And the filter assures that we don't have in this vector over here 1, 8, 1, 8, for example, right? And that's it. So, and then we collect and binary operation cannot be applied to type point, right? So we can't compare two custom types. So we have to implement something for point. Let's do that. Let's implement here partial EQ for point, and EQ takes self, or you know what, I will just copy this over here. So EQ for point, the other is of type self, and we return a boolean, right? Let's take this also as a reference. So we compare over here self dot 0 and other dot 0, and self dot 1 is equal to other dot 1, right? So when we compare a point to another point, let's say P1 is 1, 1 and P2 is 1, 1, right? Then we just compare this point with this point and this point with this point, right? Okay, and now this is working fine. So we can continue on the signal method, right? So as you can see, we get back pairs. We get here back the pairs, right? Holding every single possible combination of 2 points of the same type of antenna. And then all we do is we iterate over these pairs, right? Destructure it into 0.1, 0.2. And then we have seen already how we get the coordination of the antinodes. So for 0.1, we subtract P2 from P1 and add it to P1, right? For P2 will be, we subtract P1 from P2 and add P2, right? So we put this slice into an iter, then we filter, let's remove. And for each antinode, so this is a slice representing the two antinodes, right? For P1 and P2, right? So for each antinode, we have to check, is this actually in bound, right? And if it is, for each antinode, we just insert it into this hash set we created over here, right? So antinodes insert, and we insert the antinode. Okay, and then in the end we just return antinodes, right? That's it. So, and we have to implement this get method, fn get self, we get the point, we destructure it, and let's return an option of U8. So in the grid, we try to access X as U size and Y as U size. And that's it. Forgot in over here. And again, we can't here subtract, and we also can't add. So we have to implement this for 0.2. So let's implement add for point. Type output will be self. Fn add, we take self. So we just add the first element with the first element of the other point, and the second element with the second element of the other point, right? And let's do the same thing for subtraction. So fn sub, and here it's basically the same thing, but plus will be minus, right? Like this. Okay, now this should actually be working. Let's put this into braces. like this, because insert will return a boolean. Okay, that is it, right? So we call the signal method, we get back hash set, and then what we need is just the count, right? So we can do length and as u32, right? Then we can return some count. Let's see if this is working. Okay, we get back 14. This is correct. Now over here, we can actually put this all together in this sum. So we create a map from input, right? And then we will get back map, so we can call the signal method, and then we call length because we get the hash set, and then we have to cast that into a u32, right? So let's delete the test input. Okay, 400, and let's submit that. Okay, part 1 is done. Now for part 2. Now part 2 is very similar, but there is also a big difference. Because when we check again, the antinodes of these 2 points, right, would be here and would be here, right? And we know how we can get these antinodes. But then again, in the second part, we also have to find all the positions from further copies of antinodes, right? So an antinode can get further, right? But with the same distance. So again, we go here 1 down, 3 left, 1 down, 3 left, right? And this would be out of bounds. And over here too. So let's take another example. Let's take this one, right? Here would be the antinode, 2, 1. And then from this antinode, it can create another antinode. So again, 2, 1, okay? And over here, the same thing. So 2, 1 and 2, 1, right? Or let's take this example over here. So here we go, 1, 1, 1, 1, right? And from here again, 1, 1. And over here, it would be like this, right? Each antinode creates another antinode. Like this. I hope you get it. So over here, 1, 2, 1, 2 would be out of bounds. 1, 2 would be here, right? 2, 1, 2, 1, 2, 1, and 2, 1. Like this. So it's actually pretty similar to what we did. Let me clean up here. Except if we, for example, take these 2 points, right? So we have 2, 5, and we have 3, 7, right? We know that we have to subtract, so -1 and -2, this would be the offset. Adding it to this would be 1 and 3, right? 1, 3 would be over here, right? Over here, the same thing, subtracting this from that. So 1, 2, and then 4, 9, right? Adding this to this, 4, 9, right? Now what we have to do is we have just to add the offset we have over here again to this new antinode, right? So when we add again -1, -2, then we get 1 plus -2, 0. And this would be 1, so we would have 0, 1, right? We get another antinode, right? And over here, the same thing. We add this to that, so we get 5, 11. 5, 11. As you can see, we have here the line of all the antinodes for these 2 points. And this is not too hard to achieve when we did part 1. So for part 2, let me actually take this. It would be very similar. But this time we have another method. Let me call that harmonics, because I've seen in the text they're calling this, the historians asks if you took the effects of resonant harmonics. Okay, so let's take this one. And okay, so same thing as before, we get back a hash set and we want the length, basically the amount of points of the antinodes. Let's do the harmonics method. Again, getting back a hash set of points. And again, we create a new hash set for the antinodes. We get all the possible pairs, right? And again, for P1, P2 in pairs, same thing as above. And this time we have a slice of tuples, of two tuples, with first of all the point, so P1, and then the offset. So the offset we get by subtracting P2 from P1, right? And P2, and the offset for P2 is P2 minus P1, right? So let's iterate over this slice, and then for each we get back point and offset. And then all we do is basically while self.get point. So while we are still in the grid and not out of bounds, right? Checking it with the point. Then we insert into the antinodes hash set the point, and we add the offset to the point. And we do this again, right? And in the end, we return the antinodes hash set, right? Like I did show you over here, we are just basically looping until we don't find any valid point anymore, right? Just continuing adding to the point the offset, right? And then point will become the new antinode, and then again adding the offset and so on. So cannot use plus equals, and we can actually write it like that, point plus offset. It would work, but let's actually implement that so we learn something too. This trait is called add assign. Okay, for point, and I will just copy that. Add assign, and self will be self 0 plus other 0, self 1 plus other 1. Okay, and harmonics. So this is now without errors, right? So we can add the offset to the point, and then we loop until we find until we don't find any new valid points in the grid, right, to add antinodes to. Okay, and over here the same thing. Then we get back from harmonics this hash set. We just take the length, meaning the amount of antinodes in it, or the amount of positions, and we cast it to a new 32. Let's see, do release first. Okay, I guess I didn't take the test input. $34 is correct. Okay, now we can take the real input. Okay, please. All right. Yeah, the time is not bad actually. As you can see, not bad. So submit to. And we did it, boys. See you next time.